Let's begin with a high-level look at the architecture behind the Cortex M3 and Cortex M4 processors. Both are based on the ARMv7M architecture, originally defined for the Cortex M3. When the Cortex M4 was introduced, the architecture was extended with DSP and floating-point instructions, sometimes called ARMv7EM. All details are captured in the massive ARMv7M architecture reference manual, but we'll focus on the essential programmer's model. Now we dive into the programmer's model, starting with operation modes and states. The Cortex M3 and M4 processors have two operation states and two modes. They also support privileged and unprivileged access levels, providing a basic security model. In privileged level, you can BUS access all processor resources. Unprivileged mode restricts access to certain memory regions and operations. Let's examine the two operation states. First, debug state. As shown in the figure, debug state is entered when the processor is halted, for example by a breakpoint. In this state, the processor stops executing instructions, allowing the debugger to inspect memory and registers. The other operation state is thumb state. When the processor is running program code, it is in thumb state, executing thumb or thumb2 instructions. Unlike classic ARM processors, there is no ARM state because Cortex M only supports the thumb instruction set. Now let's look at the two operation modes, handler and TH or EAD, as illustrated here. Handler mode is entered when processing an EXCEPTION or INTE or RUPT, and it always runs with privileged access. TH or EAD mode is for normal application code. It can be USB configured as privileged or unprivileged via the controller EGISTER. Next, focus on software can be US switch from privileged to unprivileged TH or EAD. A key security feature, software can be US lower its privilege in TH or EAD mode, but cannot raise it back directly. Only an EXCEPTION handler can be US restore privilege. Software can be US switch from privileged to unprivileged TH or EAD. Both modes share a very similar programmer's model, but TH or EAD mode can be US optionally use a separate shadowed stack pointer, the PSP. This allows the OS kernel stack, MSP, to be separated from application task stacks, PSP, improving system reliability. After reset, the processor starts in privileged TH or EAD mode with thumb state, using the MSP. Many simple applications never need unprivileged mode or PSP, but they are essential when running an embedded OS. Moving deeper into the processor core, we examine the REGISTER bank. Like most processors, Cortex M employs a load store architecture. Data must be in registers before processing. The REGISTER bank, shown in this diagram, has 16 registers, 13 general purpose and 3 with special roles. Next, focus on a generous REGISTER set reduces memory access and improves. This abundance of registers helps compilers generate efficient code, minimizing costly memory accesses. To summarize, the REGISTER bank consists of 16 registers. R0 through R12 are general-purpose 32-bit registers, suitable for any data operation. The remaining 3, R13, R14, R15 serve as stack pointer, linker EGISTER, and program counter, respectively. Let's take a closer look at the general-purpose registers. R0 to R12 are general-purpose, but they are not all equal. R0, R7 are called low registers and can be USB used by many 16-bit instructions. High registers R8, R12 are typically accessed with 32-bit thumb 2 instructions, though some 16-bit instructions like MOV can be US also use them. After reset, the values in R0, R12 are undefined, so initialization is required before use. R13 serves as the stack pointer, essential for function calls and exception handling. Physically, there are two stack pointers, the main stack pointer, MSP, used after reset and in handler mode, and the PROCESS stack pointer, PSP, available in TH or EAD mode. Both are 32-bit, but the lowest 2 bits are always 0 due to word alignment requirements. The controller EGISTER determines which SP is currently visible and used by the processor. R14, the linker EGISTER, stores the return address when a subroutine is called. At the end of the subroutine, loading LR into PC resumes execution at the correct place. If a function needs to call another function, it must first push LR onto the stack, or the return address will be lost. In exception handlers, LR is automatically loaded with a magic exe_return code, which triggers the exception return sequence when used. R15, the program counter, points to the current instruction. Due to pipelining, reading PC gives address +4. Writing to PC performs a branch. Because instructions are half-word aligned, the LSB is normally 0, but for thumb state it must be 1. If you accidentally write an address with LSB equals 0, the processor assumes ARM state, which Cortex-M doesn't support, causing a fault. In assembly programming, you can be US refer to registers by different names or case variations. For example, R13 can be USB written as SP, R14 as LR, R15 as PC, making code intent clearer. ARM's ASSEMBLE tools accept uppercase, lowercase, or mixed case for these REGISTER names. In addition to the REGISTER bank, the Cortex-M has several special registers. These registers manage processor status, INTERRUPT masking, and configuration. You can BUS to access them like memory. Instead, use the MSR and MRS instructions. For C programmers, CMSASCORE provides convenient wrapper functions to read and write these registers. While simple applications rarely need them, they are essential for embedded OS kernels and advanced INTERRUPT handling. Now let's explore the program status or EGISTER, which is composed of 3 distinct parts. The APSR holds flags from arithmetic and logic operations, negative, 0, carry, and overflow. The EPSR contains execution state bits, including the thumb state bit and INTERRUPT continuable instruction fields. The program status or EGISTER consists of 3 sub-registers. Next, focus on INTERRUPT PSR, IPSR current EXCEPTION number. The IPSR tells you which EXCEPTION number is currently being handled, useful for nested interrupts. This table details the bit fields of the 3 PSRs. If you compare this with the ARM7 TDMI CPSR, you'll notice the mode bits have disappeared, reflecting the different EXCEPTION model of Cortex-M. The T bit is now at bit 24, and the INTERRUPT disable bits INF are replaced by separate primask registers. Although physically separate, these 3 registers can be USB accessed as a single combined or EGISTER called XPSR. In ARM assembly, you use the symbol PSR to read or write the combined program status word. Keep in mind that IPSR is read-only, and EPSR cannot be read or written directly with MRS/MSR. Here we see the layout of the combined XPSR, accessed with the PSR symbol. You can be US read the XPSR with MRSR0, PSR and write it with MSR PSR, R0. The bit field definitions are summarized in Table 4.2. Some fields like G, E, and Q are only present in ARMv7EM. The next set of special registers control EXCEPTION and INTERRUPT masking. PriMask, FaultMask, and BSEPRI let you disable exceptions based on priority. A smaller priority number means higher urgency. These registers can be only be modified in privileged access level, unprivileged writes are ignored. Let's see how these mask registers work, with code examples using CMSIS core functions. PriMask, when set, disables all exceptions except NMI and hard fault, effectively raising the priority to 0. FaultMask goes even further, it also blocks hard fault, leaving only NMI able to INTERRUPT. BSEPRI allows selective masking, only exceptions with priority lower than the specified value are blocked. As shown in the code, you can BUS read and write these registers using CMSIS functions like __get _primask and __set _faultmask. Next, focus on CMSIS core functions provide convenient access from C. CMSIS core functions provide convenient access from C. As shown in the code, you can BUS read and write these registers using CMSIS functions like __get _primask and __set _faultmask. You can BUS also access these registers directly in assembly language using MRS and MSR. For instance, MRSR0, BSEPRI reads the BSEPRI value into R0. And MSR faultmask, R0 writes the contents of R0 into faultmask, setting the mask. Finally, the change processor state instructions offer a compact way to control primask and faultmask. For example, CPSIEI enables interrupts by clearing primask. And CPSIDF disables faults by setting faultmask, useful in critical sections. This diagram illustrates the programmer's model of the primask, faultmask, and BSEPRI registers. Notice how each EGISTER's width and function is depicted, reflecting its role in INTERRUPT masking. By default, they are all 0, meaning no masking is active. Keep in mind that faultmask and BSEPRI are not available in ARMv6M devices like Cortex M0. If you're porting code between M3/M4 and M0, be aware of this difference. The controller EGISTER is key for configuring the processor's operating environment. It controls which stack pointer is active and whether TH or EAD mode is privileged or unprivileged. On Cortex M4 with FPU, an additional bit, FPCA, indicates if the floating point unit is being used by the current context. Next, focus on, after reset, control is 0, privileged TH or EAD mode using MSP. After reset, the controller EGISTER is 0, meaning privileged TH or EAD mode with MSP. You can BUS only change it in privileged level. Modifications only allowed in privileged mode. A crucial rule: once in unprivileged TH or EAD mode, you cannot directly go back to privileged. The only way is through an EXCEPTION. The handler can BUS clear the NPRIV bit, and upon return you'll be privileged. This mechanism allows a basic security model where untrusted applications are confined to unprivileged access, protecting the system. When an embedded OS runs, the controller EGISTER is reprogrammed at each context switch. This allows different tasks to have different privilege levels and stack pointers, as shown in the table. In an OS, control is updated at context switch to assign. Next, focus on, for FPU, the FPCA bit must not be accidentally cleared. Be careful with the FPCA bit on M4, if software clears it while floating point state is active, an INTE or RUPT may overwrite FPU registers, corrupting the task. After changing the controller EGISTER, it's architecturally required to execute an ISB instruction to synchronize the PIPELINE. After modifying control. Assembly access, MRSR0, control/MSR control, R0. It returns true if in handler mode, IPSR, equals 0, or if in privileged TH or EAD mode, control NPRIV bit is 0. Next, focus on, the C function in_privileged, demonstrates checking current. This C function, in_privileged, detects if the processor is currently in privileged mode by checking IPSR and control. It returns true if in handler mode, IPSR, equals 0, or if in privileged TH or EAD mode, control NPRIV bit is 0. Now let's look at the floating point registers, available on Cortex M4 with FPU. The FPU provides 32 single precision registers, S0 through S31, plus the floating point status and controller EGISTER. By default, the FPU is disabled to reduce power consumption. You must enable it by programming the coprocessor access control or EGISTER. This diagram shows the floating point or EGISTER bank. Each 32-bit S or EGISTER can be USB paired into a 64-bit D or EGISTER. For example, S1 and S0 combine to form D0, and S3 with S2 make D1. Registers S0 or S31 can be USB accessed individually or as. Next, focus on, double precision calculations are not supported. Even though the FPU doesn't do double precision math, you can BUS still use double word load and store instructions. The floating point or EGISTER set is summarized here, including the FPSCR which manages rounding modes and EXCEPTIO and flags. The FPSCR's bit fields allow you to configure floating point operation behavior and detect errors. The FPSCR or EGISTER contains various control and status bits for the floating point unit. Even though only single precision calculations are supported, you can BUS move double precision data between memory and registers. The flags include IEEE 754 status bits like overflow and divide by zero, as well as control bits for alternate half precision and rounding modes. The FPSCR serves two purposes: controlling behavior and reporting status after floating point operations. In typical applications, you can BUS leave it at the default IEEE 754 compliance settings. The EXCEPTION bits, such as IDC and IXC, allow software to detect and handle floating point errors like inexact results or overflows. Beyond the REGISTER bank, the FPU has memory-mapped control registers. The most important is CPACR, which enables the FPU. After reset, the FPU is disabled to save power. You must write 0xF to bits 20 to 23 of CPACR to grant full access. In C with CMSIS, that's SCB CPACR equals 0xF less than 20. In assembly, you load the address 0xe000ed88, modify the bits with an ORR, and store back, as shown here. The FPU also has additional memory mapped registers for advanced control, which we'll cover in a later chapter. Table 4.5 provides a complete reference for each bit in the FPSCR, including the alternate half-precision bit and EXCEPTION flags. Before we wrap up, let's briefly highlight the behavior of the APSR flags. The APSR contains the classic N, Z, C, V flags from integer arithmetic, used for conditional execution. On M4, it also has the Q bit for saturation and GE bits for SIMD, providing richer status for DSP and media processing. These flags are essential for efficient branching and algorithm implementation. We've now covered the complete programmer's model of the Cortex M3 and M4, laying a solid foundation for your development.